Okay, let's talk about topic 4.4 on Snell's law and refraction. We're going to do a quick review of refraction and discuss Snell's law. We will also talk about something called the critical angle and total internal reflection. You might recall that there are three ways to change the direction of a wave. They are reflection, refraction, and diffraction. Let's look at refraction in a little bit more depth. Refraction is the bending of a wave as it moves from one medium to another. The bending is caused when the wave speeds up or slows down. You will recall that waves can be represented as rays. A ray simply shows the direction of a wave's travel without showing the crests and troughs. If we look at the ray in this diagram, it starts off in air, or perhaps a vacuum. The speed of light in a vacuum, as you know, is 3 times 10 to the 8th meters per second. This is as fast as light can travel. When the ray passes from the air into the glass, it slows down. This causes it to be bent towards the normal line. Recall that the normal line is an imaginary line drawn perpendicular to the boundary between the two materials. When waves go from a faster medium to a slower medium, they're bent towards the normal. So the angle of incidence, labeled here as theta sub 1, is greater than the angle of refraction, labeled as theta sub 2. Here is a different situation. When the light ray passes from a slower medium, in this case glass, into a faster medium, let's say air, it gets bent away from the normal line. In other words, the angle of incidence is less than the angle of refraction. The amount that the ray gets bent depends on the ratio of the speeds in the two media. Suppose we would like to calculate the angle of refraction. If we know the angle of incidence and the speed of the waves in the two materials, here is the relationship. The ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of the speed in medium 1 to the speed in medium 2. This assumes the wave is leaving medium 1 and entering medium 2. This relationship is called Snell's law. Another quantity you'll encounter when working with Snell's law is called the index of refraction of the material. The index of refraction is a unitless number equal to the speed of light in a vacuum divided by the speed of light in the material. The symbol for the index of refraction is a lowercase n. Here is a table showing the index of refraction for some common materials. Materials that have a slower speed of light have a higher index of refraction. Materials with a high index of refraction, such as diamond, will cause light to refract more. Here is another way you will see Snell's law written. To use this form of Snell's law, rather than knowing the velocities, we need to know the indices of refraction for the two materials. So if light is passing from medium 1, in this case glass, into medium 2, in this case let's say air, we can substitute the two indices of refraction and the angle of incidence into the Snell's law equation and then solve for the angle of refraction. In this situation where light is traveling from a slower medium into a faster medium, an interesting thing happens if we increase the angle of incidence. As the angle of incidence is increased, the angle of refraction increases, but at a faster rate. As we continue to increase the angle of incidence, the angle of refraction will eventually equal 90 degrees. But what does this mean? It means that no light will travel into the second medium. 100% of the light will be reflected back into the original medium. This property of refraction is called total internal reflection. The angle of incidence that will cause the angle of refraction to equal 90 degrees is called the critical angle, and it's written as theta sub c. To use Snell's law to solve for the critical angle, set the angle of refraction to 90 degrees, and then solve for the angle of incidence. The resulting angle of incidence is called the critical angle, theta sub c. Any angle of incidence that's greater than or equal to the critical angle will result in total internal reflection. So why is this useful to know? Well, it turns out that the property of total internal reflection is what makes the fiber optic cables that brings us the internet possible. Fiber optic cables are made of thin strands of glass. As a laser beam travels down a fiber optic strand, it bounces off the walls of the glass fiber by total internal reflection, allowing the light beam to be transmitted down the fiber, even though the fiber is bent into a curve. This is very efficient as 100% of the light stays in the strand, allowing the signal to travel long distances. I think that's enough for now. See you next time.